Right, galvanic cells, let's go. The galvanic cells are just putting redox equations into some often beakers. It is a GG, I agree. All right, an electrochemical cell is one that converts chemical energy into electrical energy. You should know that, and it's spontaneous reaction, so it happens just like that. Happens without needing energy going in. Two different half cells. So the key features we're going to go through a little bit of. So we've got an anode there, which is the site of oxidation. Okay, so anode, site of oxidation, it's where loss of electrons occurs. All right, I'm not going to go through too much of this. Cathode is reduction, so therefore it's the gain of electrons. It's a half cell here, half cell there, because it's literally half of a cell. A cell is some batteries connected together. Then you've got a voltmeter, which measures the voltage. You've got electrons flow, so that shows electrons moving there. We already said that. This is copper. This is copper sulfate in solution. So it's a solution of copper sulfate, which is why it's blue. If you've ever seen them, you might not have had a lot of time at school last year, but you might have seen, if you did a prac with it, copper sulfate's blue, whereas zinc there is a clear solution. Then you've got a salt bridge here, which is literally a piece of paper that's like a bridge with salt in it. Okay, and so this here, I'm going to go a different color just to make it clearer. This is the external circuit. So it's a bit of physics. So it's a circuit because it contains electrons moving around or electricity. And this is the internal circuit. So when I use those words, that's what I mean. And you might hear those later on. Okay, so it flows charge. A circuit is important for charge or electricity moving, but charge is the more correct answer in this point. All right. So they're the basic components. Daniell cell, that means zinc and copper, very common. You'll expect to know that term. It'll come up lots. You'll remember it. Okay. Solid zinc and copper, they're called electrodes because they conduct electricity. And the surface is where the redox reactions occur, and that's where electricity is made or generated. Okay, the electrodes can have a reacting metal, or they're called inert. So inert, anyone know what that means? What does inert mean? That's another term you should know, or at least we're learning it now, so you should know. Yeah, non-reactive. Okay, so it means it won't react with anything else in the atmosphere or anything else. So platinum is a good example of inert metal, which is why they use platinum in surgeries. If you look at people who have plates and the likes, like titanium sometimes and platinum, and they don't react with the body. Platinum can't be oxidized, it doesn't rust. Very expensive, but doesn't rust. Okay, so inert metals, they don't rust, they don't react. Okay, so that term is expected to be known. All right, anode, oxidation, cathode, reduction. Cathode is positive and anode is negative. And that's because it's the source of the electrons. All right, so electrons are negative charge. So if the electrons come from the anode, add gas through a pipe. I don't know exactly what you mean. It's raining now. When did that happen? It started raining. Wasn't it like 22 today? Oh, that's disappointing. So the source of electrons is a negative charge. Just seeing if anyone's listening. No one's listening. No one cares about the rain. That's devastating. It was sunny. Yeah. I like rain too, but So source of electrons is the negative charge. That's why the anode is called the negative electrode. And then the positive electrode is where the electrons are going to. All right, they're in an electrolyte. I don't think that's awkward, but yeah, sure. The electrolyte is where you've got a solution and it conducts electricity, so it's got ions in it. You might remember that from Unit 1, 2. And then they're connected by a wire. All right, cool. We're going through that. External circuit, we kind of did that. External circuit's where the electrons go via a wire. and you can see zinc loses electrons. There's an electron going through the external circuit. Zinc's being oxidized to zinc 2+. And then that metal disappears. So that solid there corrodes away. Like you imagine that where the red that I've just highlighted, that goes away. And then for the copper, it starts to gain electrons from the external circuit. So electrons are coming down from the wire there. And then you get copper from solution. So this is a copper ion. That copper ion there deposits or is placed on the outside of the electrode there. There's a Daniell cell. All right, so internal circuit. I'm going through a bit quicker because of time and because I want to get to equations. All right, internal circuit is where we have, when the cell's making energy or producing electricity, zinc moves into solution, meaning, so here, the solid zinc that we had at the start goes into zinc ions, which dissolve in the water there. That's aqueous, if you can read my writing. We'll try again. All right, and then for the copper, we've got copper ions gaining electrons and forming copper solid. So here we're getting more and more positive charge because there's more and more zinc ions. So the positivity or the amount of positive gets bigger and bigger and bigger and bigger. You get more and more positive. Whereas over here, maybe, but I don't know. No, calorimetry, no. That's in later on, Unit 4. Yeah. Okay. So zinc there, more positive into the beaker. Whereas over here, this was positive, but now it's becoming more negative, or it's becoming less positive because there's less of the copper ions here, and there's more electrons coming in. So if you imagine that, if we kept having the negativity increase or less positive over here, and we kept having more positive over here, eventually we're not going to get any more zinc coming out because zinc is a positive ion. We're not going to put more positive in there. There's going to be too much positive in one side and not enough on the other. So we use a salt bridge, an internal circuit, to help us solve that issue. It's filter paper. So you might have seen filter paper. It's just like, if you look at drip filters, coffee, that's filter paper, and it's soaked in an unreactive ionic salt. Most often, it's potassium nitrate. As you can see here, it's got nitrate and potassium because it's always soluble. It always dissolves in water, and it doesn't react with anything else. So that's a good one to have, potassium nitrate. All right. Anions, remember they're negative charge, so like chlorine is an example of an anion, and then cations, like I just did calcium, just chose it, they're positive charge. So example chlorine, example calcium. Okay, we're going to move through that. Here we go, question 15. I think I've got a poll for this one. Just check the questions. Questions. Poll 15. Is it here somewhere? No. All right, I'll just type it in quickly. So have a look at question 15 and tell me what you think about the galvanic cell. As soon as I publish the poll, I'm just chucking it in now. Question 15, dates, start, and bang. Galvanic cells consist of two half cells, an external circuit and an internal circuit, which is true. We're all 50-50, 46-48, 47-47. So electrons flow away from the anode and anions migrate towards the cathode. That's both true. And anions, remember, they're negatively charged. So it was just up above. Anions move to the anode and cations move to the cathode. So C and C, anions and anode. So therefore the answer is D. Nah, you would think that, but we're talking about in the salt bridge. Talking about in the salt bridge. To try and balance the charge. Yep, good question. Just always use potassium nitrate. You'll never, ever, ever, ever be wrong if you use potassium nitrate. Unless it says you can't use potassium nitrate, this salt bridge will always be an answer that's correct. You can use other things. You can use like silver chloride, but the problem with silver chloride is that it's insoluble in some circumstances. You can use, any ionic solid. You could use sodium chloride, but again, you might have some instances where it's insoluble in water because it forms a precipitate, and you'll get to that later. All right, so 15 is D. Let's move on. Excuse me. All right, 16. Timing, yeah. What referring to the salt bridge? Because it's talking about an internal circuit. Okay, so this is a good one to practice. We're not going to go through all of it because of time, but you can see here, you can look at the oxidation number and look at what's undergoing oxidation, okay, and what's undergoing reduction. So if this is the negative electrode or the negative electrode, that's going to be the anode. I'll just tell you that so it makes it easier. And this is the cathode, so it makes it easier. So if we go back up here, what's undergoing oxidation and what's undergoing reduction? What's undergoing oxidation and what's undergoing reduction in this instance? Oxidation is magnesium, awesome, because it goes from 0 to +2, whereas silver goes from +1 to 0. So this must be undergoing oxidation. Cool, just making sure the is recording there. Okay, so then this is undergoing reduction. Then, now we know that. Yep, awesome. Now we know that, we can assign. So the anode is a site of oxidation, remember? So if anode's a site of oxidation, as we did before, and cathode's a site of reduction, we can see that silver is going to be over here. So that's going to be silver metal. Okay, and then over here, this would be what metal? What metal's on my left? Magnesium, Mg, solid. And same as Ag, solid. All right, so that's there with those, where those arrows are. Cool. Salt bridge, potassium nitrate. Just stick with it, much easier. Now, which way are the electrons flowing? You need to draw arrows. Right, so there, label with an E on top, so we know, excuse me. So here we could have silver nitrate or silver chloride or any form of silver, as long as you've got silver in there in solution. Yep, clockwise is a good one. And then this one, you could have magnesium nitrate as well. You'd need 2 of them. You could have magnesium chloride. It doesn't matter. It's just an ionic compounds which dissolves in water. You'll see more of these. You'll do lots of these, okay? You'll see, and you'll get used to what kind of solutions they form. All right, so we haven't done half equations. We've done electrodes and polarity, we've done electron flow, electrolyte, and the salt bridge movement of its ions. So over time, magnesium is going to lose electrons. Magnesium is going to go from solid to, if I can get the line straight, magnesium 2+, which means you're getting an increase in positivity. It's losing electrons, but I'm saying in here, it's becoming more and more positive over time because you're getting more and more magnesium ions. Whereas over time, the silver, so more and more magnesium ions coming from the solid magnesium, whereas over here, the silver is depositing on the outside, so you're getting less and less silver over time, and you'll be getting an increase in mass. Okay, so do the same equation. Silver there, ions, plus an electron, aqueous there, goes to silver solid. So over time, it's getting less and less. So here we've got more positive And here we're going to get less positive or more negative. So because it's getting more positive, good point. Potassium nitrate's not negative, good pick up. So because it's getting more negative there, we need to balance out the negativity, the negative charge. So the potassium is going to flow this way to make it more positive, increasingly positive over here, because if it's not positive enough, the electrons can't flow. And then therefore the nitrate is going to move over here. The reaction stops when you run out of metal or there's not enough difference in electrical charge. Electrolyte is just a solution that conducts electricity. All right, you're going to practice more and more of this, but that's the basics there. All right, I want to move on because of time.